In this video, I want to discuss some strategies for evaluating limits. In the first place, we almost always want to start when we're evaluating limits is by just applying direct substitution. If you recall from the last lesson, that just simply means we're going to evaluate the function at the x value where we're evaluating the limit. So we're just going to plug in whatever c is into our function and see what we get. Now, sometimes that just gives us the limit value, but a lot of times we'll often find that we end up with something called indeterminate form. And if you recall from the last lesson, indeterminate form often takes on the form of something like 0 over 0 or infinity over infinity or some undefined value over 0, something like that. And indeterminate form does not mean that the limit doesn't exist or that it is undefined. Rather, it's simply telling us that we cannot gather information about what the limit is in its current form. It is indeterminate. We cannot determine the limit in this form. That's literally what it means. So what that then means for us is we need to then resort to some other tactic or strategy to evaluate the limit. And I've got 4 listed out below here after direct substitution fails. And each of these problems that I'm going to go through in this video will hopefully highlight how to apply one of these strategies. And I encourage you, as we go through each problem, pause the video and refer back to this list and ask yourself, okay, which of these techniques would seem to make the most sense here if direct substitution doesn't work? And one other note before we start a couple of these problems, I want to make sure that we're really clear about some of our notation. Since we're going to be working with limit notation, we want to make sure that we're understanding when exactly we can stop writing the limit statement and when we want to make sure we do have them. So hopefully I can make that clear to you as we go along. All right, let's start with this first problem here. So this first problem is asking us to find the limit, and let me just focus in on this. And the first thing we want to do is we want to try to apply direct substitution if we can. So we're going to go ahead and plug in 2 into this function and see what we get. So we got 2 minus 2 all over 2 cubed minus 2 times 2 squared plus 2 times 2 minus 4. Okay. So evaluating this, we're going to get the following statement. We got 0 over, and just doing some quick math here, yep, that does indeed come out to 0. So we have indeterminate form, which again, just simply tells us that we cannot determine the limit with a function currently being written in this form. One thing that I want to point out to you, and just make sure that you're really careful about, is that you're not saying that this limit is equal to 0 over 0. We don't want to do that, okay? And the reason for that is we're not saying, well, we shouldn't be saying that this limit is equal to 0 over 0. There may or may not be a limit here. We don't know if it exists, but it's not equal to 0 over 0. Because later on, if we complete this problem and find out that there is a limit, we're creating a false statement here. We're saying it's equal to 0 over 0, and it's equal to something else, which isn't the case. So just be careful about writing an equivalent or equal statement with indeterminate form. We're showing this work to here just to indicate to the reader or to anyone else that we've tried direct substitution, we've ended up in indeterminate form, so we're going to have to try something else. All right, so what is that something else that we're going to try? Well, let's go ahead and again, pause the video, ask yourself what would probably make the most sense. And in this case, we're going to try dividing out technique. So what that means is I'm going to say, all right, the limit that we have above is equal to this limit that I'm about to write here. We've got the denominator that I want to factor, because I'm hoping to divide out a factor in the numerator and denominator. So factoring by grouping here makes sense. So x squared times x minus 2 plus 2 times x minus 2. And let's extend that out as well. Well, let's clean that up a little bit. And if I factor out that x minus 2, I now see something that I can divide out from both the numerator and the denominator, which now allows me to then write that this limit is equal to the following. okay? So let me pause for a moment here and just make sure that we're clear about what just happened. I am not saying that this function is equal to this function. They are not equivalent functions. Let me just zoom out a little bit. They're not equivalent functions. Their graphs are going to look remarkably similar. The only difference being that this function up here is going to have a hole at x is equal to 2. So other than that, the graphs are going to look the same. However, they are not equivalent functions. They are different. What we are saying, however, is that this limit statement here is equal to this limit statement here. Their limits are equal. In other words, they will have the same y value that the function approaches as x approaches the value of 2. They are equivalent limits. They are not equivalent functions. I just want to make sure that we're clear on that. One other thing that I want to highlight here is so far notice that every step of the way that I have written down limit statements. And this is my way of indicating that this limit here above, our original limit, is equal to this limit. It's equal to this limit. And it's equal to this limit. I'm coming up with equivalent limit statements. If I went ahead and I wrote this here, now this is a false statement. Notice, this limit here is not equal to 1 over x squared plus 2. That's a function. It's not the limit of what I have in the previous step. So if I disregard that limit statement here, I'm coming up with a false statement. So I want to make sure I'm really careful about writing the limit each step of the way. That's probably one of the most common mistakes I see for students who are just starting out evaluating limits. Now that I've got an equivalent limit statement, I'm going to go ahead and see if I can apply the direct substitution here. In other words, I'm going to just evaluate this function that I have now at x is equal to 2. So I've got equals 1 over 2 squared plus 2, which is equal to 1 over 6. So ask yourself, do I need a limit statement here? And the answer is, well, it doesn't really matter. But here I can disregard the limit statement because I am saying the limit of this is indeed equal to the value of 1 over 2 squared plus 2, which is equal to 1 over 6. Had I written the limit statement here, what is the limit of this statement here as x approaches 2? Well, it's still going to be 1 over 6. So writing the limit statement there doesn't really matter, but typically once I get to the direct substitution part, I just disregard that limit notation. So I can just go ahead and now say the limit of this function as x approaches 2 was indeed 1 over 6. All right, now let's try another problem. So we've got this one here. And again, we're going to start with the direct substitution, see if that does anything for us. So we've got 2 to the 4th minus 2 times 2 squared minus 8 all over 2 to the 4th minus 6 times squared plus 8. And just doing some quick math, we see that this is equal to 0 over 0, which is again indeterminate form. Notice I'm not saying that this is equal to 0 over 0. No, I'm not saying that. All right, I'm saying what I've just done direct substitution with gives me some indeterminate form. Therefore, I know that direct substitution doesn't work right now with the function currently the way it is. So again, I'm going to try the dividing out technique and see what we can do here. So we're going to say this is equal to the limit as x approaches 2. And let's go ahead and factor that numerator. Well, we can just factor that quartic up there as a quadratic. So that would give me x squared plus 2 over x squared minus 4. And in the denominator, I've got x squared minus 4 times x squared minus 2. Well, let's take a look at that. I've got a common factor of x squared minus 4 in both the numerator and the denominator. So we can say this is equivalent to the following limit. And now let's see if direct substitution does anything here. Well, this should be equal to 2 squared plus 2 over 2 squared minus 2, which would just give me 6 over 2. And that's equal to 3. Okay, so voila, we found our limit. We did some nice work to that function there and divided it out a common factor that was causing the numerator and denominator to be equal to 0. And we came up with an equivalent limit statement, and that's equal to 3. All right, let's go ahead and try a few more problems. All right, so in this problem here, look, we're going to try the direct substitution again. And I'm not going to write equals, but I'm just going to go ahead and plug in 3 into this function, and I'm just going to save us some time. And turns out this is 0 over 0, or indeterminate form. Okay, and if you don't believe me, try it out. So we've got a rational function here, and we're going to need to find some way to rewrite this function and come up with an equivalent limit. And at first thought, I might be tempted to sit there and say, oh no, I might have to apply the possible find the possible rational roots, right? So remember that P over Q test, right? So plus or minus 1, plus or minus 2, plus or minus 3, and so on. I'm not going to list them all out. So we could do that. However, we're given a huge hint here. The fact that when we tried to do the direct substitution and we were evaluating 3 at x is equal to 3, by plugging in 3 into the numerator, we ended up with 0. By plugging in 3 into the denominator, we also got 0. So ask yourself, what does that then mean for us here? It means that x minus 3 is a factor of both the numerator and the denominator. In other words, 3 is a 0 of both the numerator and the denominator. So that's a huge clue for us. That tells me that I should be able to divide both the numerator and denominator by x minus 3. So let's go ahead and just do some synthetic division here. So I'm going to take the coefficients of the numerator, 1, negative 4, negative 3, and 18. And if 3 is a 0 of both, we're going to write 1. That's going to give me 3, negative 1, negative 3, negative 6, negative 18. And that confirms for us we got 0. And I mainly did that just so that I could get these coefficients here. So that then tells me I've got x squared minus x minus 6. In other words, I can now write my numerator as, and let me just change the color here so that we don't get too mixed up. So now I can write my numerator as the following. X minus 3 was a factor of the numerator, and we're left with x squared minus x minus 6. Now, let's also do some synthetic division for the denominator now. So we're going to go ahead and go 1, negative 4, 1, and 6. Again, divide this by 3. 1, 3, negative 1. Okay, and that means I can do my denominator as the following. Again, x minus 3 is also a factor of the denominator, and that then leaves me with x squared minus x minus 2. So right away, I can go ahead and I can clean this up and come up with an equivalent limit statement. And you could try the direct substitution there, and maybe mentally you just want to go ahead and try plugging in 3 right now. That would give us 9 minus 3, which is 6 minus 6. That gives me a 0 in the numerator. That in itself isn't a problem. But try plugging in 3 into the denominator using direct substitution. That would give us 9 minus 3, which is going to be 6 minus 2. Oh, we're actually okay here. So let's go ahead and just do that. So let's write, and that's going to bother me that it's not exactly the same purple color. All right, we got the limit as x approaches 3 of x squared minus x minus 6, x squared minus x minus 2. If I plug in 3 here, what do I end up with? That gave me 0 over 4, so that was indeed equal to 4. So the limit here is 0. So we're okay. Some of you might be asking whether or not you could have actually factored this further. And yes, you could have. This would have given me x minus 3 times x plus 2. And this would have given me x minus 2 times x plus 1. So you could have factored it further, but honestly, you don't really need to. If you can apply direct substitution and get a limit and it's not indeterminate form, then you're set. There's really no need to continue on. But if it bothers you, you could have come up with another limit, equivalent limit statement. Okay? All right, let's try our next problem. Again, pause the video, ask yourself which strategy would appear to make the most sense here if direct substitution fails. So might as well figure out what this is using direct substitution. So we're going to go ahead and the square root of 0 plus 9 minus 3 over 0. And we're left with indeterminate form. So hopefully you've had a chance to ask yourself which strategy we would want to use. And this is the one where we're going to want to multiply by our conjugate. So we're going to write the following. Let's change colors here. Let's choose green. Equals the limit as x approaches 0. And we're going to take this function that we have and we're going to multiply it by the conjugate of this numerator here. So we're going to multiply this by the square root of x plus 9 plus 3. And remember why we're doing this. This is going to help us get rid of or negate that radical in the numerator that might be causing us issues. So cleaning this up here, this is going to give me, this is just a difference of squares. So the square root of x plus 9 squared, well, that square root has now been negated. So we've just got x plus 9. And negative 3 times positive 3 is going to give me negative 9. Now in the denominator, I've got a radical here, but let's not be worried just yet. And I know some of you are getting the cold sweats right now just because you're seeing that radical in the denominator. Let's not worry about that right now because all we're worried about is evaluating a limit. So cleaning up the numerator, we see here that this positive 9 and this negative 9 are going to negate one another. So I can now write the limit as x approaches 0. Oh, and I see something else that also can be divided out. This, now that I have just an x in the numerator, I can divide that out with this x. So what we're left with is just 1 in the numerator over the square root of x plus 9 plus 3. So try the direct substitution now and see if we get a limit. Well, when I plug in 0 into the denominator, well, that's just going to give me the square root of 9, which is 3. 3 plus 3, last time I checked, is 1 over 6. So I didn't have to worry about that square root at all. I've got a nice limit coming out of this, and I did that by multiplying by the conjugate. All right, now let's try our last problem for this video. I'm going to go ahead and just try the direct substitution now. And when I plug in 0 here, I'm going to end up with 1 over negative 8 plus 1 over 8 and over 0. And this is going to give me, if I'm not mistaken, 1 over 8. Oh, there's just 0 over 0. So again, indeterminate form. And you know what? Now that I'm at this, I think I realized I made a mistake earlier. I think I may have said something like undefined over 0. Let's stay away from that comment for now until we've had a chance to talk about more forms that are indeterminate later on in calculus. Okay, so going back to this. Now that we know that we're in indeterminate form, let's think about what strategy we're going to do. Oh, I made another mistake. This is not our last problem with this video. Sorry, there's one more at the bottom. Forgot about you, number 6. I'll get back to you in a bit. All right, so let's go ahead and try this one now. I'll change that color. What can we try? Let's try pink. Pink doesn't get enough use in these videos. All right, so for here, we're going to go ahead and we notice we have a complex fraction, which is just a way of saying we've got a fraction within a fraction. In this case, we have a couple fractions within a fraction. So we're going to go ahead and we're going to simplify the complex fraction, which means we're going to say the following. The limit as x approaches 0 of 1 over x minus 8. I'm just going to write down our original complex fraction. we're going to multiply both the numerator and the denominator by the least common denominator of our complex fraction. So specifically the part here where the complex fraction is, or what's causing the fraction to be complex. So we've got 8 and x minus 8. So we're going to multiply the numerator and denominator by that. By the product of that, I should say, which is our least common denominator. All right, so now let's see what that cleans up to. So we've got, if we multiply all of this by that, we should be left with 8 plus x minus 8. And in the denominator, we should have 8x times x minus 8. Okay? So let's clean this up a little bit. And you know what? We didn't need those parentheses. So hopefully you now see that we've got an 8 and a negative 8. They're going to negate one another. And I also see an x up now in the numerator that can be divided out with this x. And so we're left now with 1 over 8 times x minus 8. And this is just making our lives a little bit easier when we're going to try the direct substitution. So now that we have this, we've got, let's see, 1 over 8 times 0 minus 8, which is negative 8, which is negative 1 over 64. And this gives us our limit. Okay? Now, again, there are a number of equivalent limit statements here. And ask yourself, what if I had tried to do direct substitution perhaps up here, for example? Well, again, prior to me cleaning that up a little bit, take a look at that and just maybe even mentally ask yourself what would have happened had I tried to plug in 0. The fact that I had an x in the numerator and an x in the denominator right away tells you I'm going to have a 0 in the numerator and a 0 in the denominator. So you had to clean up that function. All right? Okay, so now let's try the real last problem. And there's a little bit of a typo there. Just pretend that wasn't there. All right, so try the direct substitution. The sine of pi over 2 is going to be 1. So 1 minus 1 over the cosine of pi over 2, which is 0. Well, that's equal to 0 over 0. So again, indeterminate form. So given that this is a problem dealing with trigonometry, probably tells us that we're going to need to apply some trigonometric identities. So let's just stick with black for this one. The limit as x approaches pi over 2 of 1 minus sine x over cosine x. And think about some identities that we might be able to apply here. And there's more than one way to do this. I'm going to go ahead and multiply by the conjugate of the numerator in the top and bottom. So basically multiply this as such. Now, what does that do? This, and we can just say this, equals the limit as x approaches pi over 2 of 1 minus sine squared x over cosine x, and I'm not going to distribute this just yet because I want to see what happens after I apply perhaps another trig identity. So 1 minus sine squared x, do you remember what that's equal to? I'm sure you do. So the limit as x approaches pi over 2, that's equal to cosine squared x. If you remember your Pythagorean identities, cosine x, 1 plus sine x. And now we can divide out this cosine x with one of the two cosine x's up here. So let's go ahead and continue this over. So this is equal to the limit as x approaches pi over 2 of 1 over 1 plus sine x. So the fact, not 1 over, we got cosine x over 1 plus sine x. So let's see where this leaves us. If I take the limit of the numerator as x approaches pi over 2, cosine of pi over 2 again is 0. So cosine, let's write this, cosine of pi over 2 over 1 plus sine of pi over 2. That gives me 0 in the numerator. And in the denominator, sine of pi over 2 is equal to 1. So we're actually set. 1 plus 1, we can say this is equal to 0. So 0 is a totally fine and valid limit. And again, it looks kind of funny, but I'm going to leave it because why not? Okay, so hopefully this helps highlight some of the different strategies for